And so what we're going to do is we're going to save the last thing for balancing redox reactions, because these can be really tough. So we're going to start off simple, and they're going to get a little bit harder, and I will walk you through it. It is a little tricky sometimes, but it starts off pretty easy. So balancing single replacement redox reactions that are written in net ionic form. Okay, so they're not written like what we did back in the fall when we were doing single replacement reactions. So, oops, somehow got out of order. Weird. All right, so when you balance redox reactions, first thing, atoms of each element must balance. Well, you guys are used to that. We've done that before. This is the new thing. The total charge on each side of the arrow must balance, meaning the number of electrons lost has to equal the number of electrons gained. So to balance the redox reactions, we're going to write the half reactions. Well, we've been doing that. We did that for figuring out which one's been reduced, which one's been oxidized. We've been doing that to find the galvanic cells. And then here's the thing. You're going to multiply by coefficients to make sure that the electrons lost by one element equal the electrons gained by the other. You want to make sure it's balanced. You're going to use the least common multiple. Okay, now I'm throwing a math term at you. Don't panic. Okay, I'll show you how it's done. So, balance the half reactions below, the equations below using the half reactions method. So, Fe, Fe, one atom, one atom. Gold, gold, one atom, one atom. So if I'm going to balance it using half reactions, I'm going to write them as separate. Okay, I'm going to put the electrons in, and remember this is an element 0, element 0. So I have to put 3 electrons here to balance the charge. I have to put 1 electron here to balance the charge. Remember, electrons are negative. This is the hardest part. The electrons are negative. That's positive 3. It takes 3 of those negatives to make it 0 overall. Then I want to make sure that the electrons lost by one equal the electrons gained by the other. So I'm going to use the least common multiple of 1 and 3. Means a number that they both go into, that is the smallest possible number they both go into. And I'm going to multiply that by 3. And when I do that, I get 3 electrons plus 3 Au1 plus goes to 3 Aus. Everything got multiplied by 3. Then I'm going to add them back together. And when I do that, the electrons are going to cancel out, and they're supposed to. Things on the left side of the arrow stay together. Fe, 3 Au1 plus goes to Fe3 plus and 3 Aus. And just to check and make sure, I have 1 atom of Fe, 1 atom of Fe, 3 atoms of Au, 3 atoms of Au. Total charge on this side is 0, and 3 times 1, positive 3. Total charge on this side is 3, and 3 times 0, positive 3. So that's a balanced redox reaction. That's how you do it for single replacement. Okay, so I'm going to erase the ink. I'm going to go ahead. I want you guys to practice this one. This is the one we were talking about all along. You have aluminum going to Al3 plus, and you have Cu2 plus going to Cu. Okay, and again, elements in their standard states are 0. So for this one, to make the charge balance, figure out how many electrons. For this one, to make the charges balance, figure out how many electrons. Okay, this would be 3. This would be 2. Then you want to find that the number of electrons lost by the aluminum are equal to the electrons gained by the copper. So we're going to do the least common multiple of 2 and 3, a number that they both go into, that is the smallest possible number, 6. So I'm going to multiply that by 2, multiply that by 3. I'm going to rewrite it. 2Al goes to 2Al3 plus 6 electrons. 6 electrons plus 3 Cu2 plus goes to 3 Cu. I'm going to add them together. The electrons are supposed to cancel out. One's being oxidized, one's being reduced. I have 2Al, 3 Cu2 plus goes to 3 Cu, and 2Al3 plus. Just to check and make sure, 2 atoms of aluminum, 2 atoms of aluminum. 3 atoms of copper, 3 atoms of copper. But the charge is the biggest thing. 0 times 2, 3 times 2 is 6. 0, 3 times 0, and 2 times 3 is 6. So it is a balanced redox reaction, atoms and charge. I'm erasing again. Oops, maybe not. It's all right. Now, what happens if we have some of these more complicated redox reactions, not just single replacement? Well, there's a lot of redox reactions that are not single replacement, and I'm going to show you guys how to do this. Most of them take place in acidic solutions. That means we're going to see H plus, and we're going to see water. Solution means water, acidic means H plus. There are several steps needed to correctly balance these reactions, okay, and you have to follow them in order, okay? So the first step is you're going to write the half reactions. I think you guys can do that. We've been doing it for 3 lessons now, okay? Then here's the trick. This is where the steps kick in. You're going to balance the atoms other than oxygen and hydrogen, so your aluminums, your coppers, your iron, whatever. You're going to balance those guys first, okay? Then you're going to balance the atoms of oxygen by adding water, because most of these take place in water. So for every oxygen atom you need 1 water. Then you're going to balance the hydrogen atoms by adding H with a positive 1 charge. I'm sorry, these are not subscripts and superscripts. So for every H you need, you're going to add an H1 plus, because it takes place in acidic solution. Then you're going to balance the charge by adding electrons, and that's what we were doing on the previous slide. We were figuring out how many electrons we had to put in. This is a little bit trickier on this one, a little bit. And then you're going to make the electrons lost equal to electrons gained by finding that least common multiple and multiplying each half reaction to get the least common multiple of the electrons. You're going to add them back together, and we've done that. We did that on the previous slide. Now here's a big thing. You're going to cancel out duplicates. You'll see what I mean with that. And then you're going to double check the atoms, which we've done, and double check the charge, which we've also done. So some of the steps are new. These are new, and that's pretty much the duplicates part was new. But everything else is stuff we've done in the previous slide. So here we go. Break them into the half reactions. Fe2 plus goes to Fe3 plus. Then I have Mn O4 1 minus goes to Mn2 plus. Now you will make your life a whole lot easier when you're doing this if you copy correctly. If you forget this 1 minus, things are not going to turn out so nice for you. It's really important to copy correctly. Okay, so first step, break them into half reactions. Second step, you're going to balance the atoms other than oxygen and hydrogen. Fe, Fe, 1 and 1. Done. Easy, right? Mn and Mn. Done. Number of atoms is the same for everything. Now, next step, balance the oxygens by adding water. Well, in this first half reaction, there is no oxygen, so I can skip that step for it. However, here I have 4 atoms of oxygen, so I need to put in 4 water molecules. 4 times 0 gives me those 4 oxygens. Okay, I'm going to erase that little arrow. All right, next step. You're going to balance the hydrogens by adding H1 plus. And again, no hydrogens, skip it. Here I have 4 times 2, I have 8 hydrogens, so I'm going to put 8 H1 plus over here. Okay, so far so good. Now you're going to balance the charge by adding electrons. If I look at this, the charge is positive 2. I look at this, the charge is positive 3. Electrons are negative. They bring charges down. So if this is positive 3, to bring it down to positive 2, I have to add the electron to that side. And I only need one of them, because it will bring the charge down from positive 3 down to positive 2. This reaction is a little bit more challenging. So water as a compound has a charge of 0. If I look at the total charge here, I have 4 times 0 and positive 2. It's positive 2. Over here, on the other hand, I have 8 times positive 1, and negative 1. So what that leaves me with is positive 7. And yes, you have to be pretty good with number lines. Okay? So positive 7 on one side, positive 2 on the other side. Electrons bring charge down. If this is positive 7, I need to bring it down to positive 2 by adding 5 electrons. Okay? So I'm going to erase this part. I'm going to erase that part. So the next step, So you want to find the least common multiple of your electrons. 5 and 1. The least common multiple would be 5. I'm going to multiply this by 5. So I have 5 Fe 2 plus goes to 5 Fe 3 plus and 5 electrons. Seventh step is to add the reactions back together and cancel out anything that is a duplicate. The electrons are necessarily and required to be duplicates, so they go away. So rewriting it, I have 8 H1 plus, 5 Fe 2 plus, MnO4 1 minus goes to 5 Fe 3 plus, Mn 2 plus, and 4 waters. Okay, so doesn't matter the order you write them in, as long as they're on the correct side of the arrow. That's one thing. Next thing, you want to check your atoms to make sure your atoms are balanced. I have 8 hydrogen atoms, 8 hydrogen atoms, 5 Fe, 1 Mn, 1 Mn, 4 O's, and then 4 times 1 is 4 O's. So my atoms are good. Let's check that total charge. I have positive 8, positive 10, and negative 1. Together, that's positive 17. Over here, 5 times 3 is 15, positive 2, and this is 0, so 17. So is a balanced redox reaction. These are hard. Absolutely, these are hard. Okay, I will expect my students, that would be Mrs. Packard's students, to be able to try it. Okay, I haven't decided yet. We'll see how it goes. We'll try it, see how it goes. Leave it at that. And then I'm going to show you a hard one, and this is something I would expect AP students to be able to do. I will not expect first-year students to be able to do this, because this one's a little harder. So, break them apart into the half reactions. IO3, 1 minus, goes to I2, NO, goes to NO3, 1 minus. So if you want to stop the movie right now, that would be okay. All right, unless you're planning on taking AP and you want to see how it's done, I'll show you. All right, half reactions first. Then you balance the atoms other than oxygen and hydrogen. I have 1 I, and I have 2 I's. I need to put a 2 there first. If you forget this step, you are screwed for the rest of it. All right, so you balance the atoms other than oxygen or hydrogen. Then you balance the oxygen atoms by adding water. 2 times 3 is 6. 6 waters over here. I have 1 oxygen on the left, and I have 3 on the right. That means I need to put 2 waters there. Not 3, because 2 times 1 and 1 is 3. Then you balance the atoms of hydrogen by adding H1 plus. I have 2 times 2 is 4. 4 H1 plus. 6 times 2 is 12. 12 H1 plus. Then you balance the charge by adding electrons on each half of the reaction. This side is 0. This side is positive 12. Minus 2 is positive 10. So I need 10 electrons, because electrons bring charge down. This side is 0. This side is negative 1 and positive 4. So it's positive 3. I need 3 electrons here. Then you find the least common multiple of your electrons. 3 and 10, that would be 30. I'm going to multiply this by 10. Multiply this by 3, and I'm going to rewrite them. So 30 electrons plus 36 H1 plus 6 IO3 1 minus goes to 3 iodines and 18 waters. That one's done. This one I'm going to multiply everything by 10. 20 H2Os plus 10 NOs goes to 10 NO3 1 minus, 40 H plus, and 30 electrons. So I'm going to add them together and cancel out things that are the same. First of all, the electrons always will cancel out. Now you might notice that I have some H pluses on opposite sides of the arrow. I have 36 on the left and 40 on the right. What that does is these go away. It leaves me with a net of 4 H pluses. I also have 18 waters on the right and 20 waters on the left. That leaves me with a net of 2 waters. So when I add them together, I get 2 water, 10 NO, 6 IO3 1 minus goes to 3 I2s, 10 NO3 1 minus, and 4 H1 plus. If you check your atoms, there's 4 hydrogens and 4 hydrogens, 10 N's and 10 N's, 6 I's and 6 I's. The O's are a little tricky. 2 plus 10 is 12, plus 18 is 30, 10 times 3 is 30. Total charge, 0, 0, negative 6. Total charge here is 0, negative 10, positive 4. Charge balances. That is the balanced redox reaction. Like I said, that's a tough one. Don't expect you guys to do that. It's okay. All right?